Hey everyone, welcome back to physics. This will be lecture 8 of the course, and in this section we're going to discuss really our first big 2-3-dimensional kind of motion, and that is the famous projectile motion. So let's go ahead and jump into it. So we'll call this section 2.2 projectile motion. So what is a projectile? Well, a projectile, we can think of a projectile as basically any object or body that is given some kind of an initial velocity, and then after that initial velocity, its motion follows a path determined entirely by gravity, okay, and sometimes air resistance, right? So a projectile, let's write this down. So a projectile is any body that is given some initial velocity. So some initial velocity, and then follows a path determined entirely by gravity. Okay, and so this is this should be a familiar concept. You throw a ball in the air, projectile motion. You drop something off of a roof, projectile motion. Maybe the most familiar example would be like the cannonball example. So I've got a cannon, and it fires some kind of a cannonball out of it, right? And so the cannonball is given some initial velocity, right, by the cannon, namely. But once it exits the barrel of the cannon, its path is determined 100% by gravity, right? And certainly in the case of a cannonball, air resistance is negligible. But this thing is flying through space, and it is being it has a path, a familiar path. We know it goes up for a while and then comes down and hits the earth again. Very familiar path. That path is determined entirely by gravity. So that's really the key to projectile motion, is that its path is determined entirely by gravity after an initial velocity is applied to it. Right? So a cannonball is a familiar example. Okay. Now, as I said at the onset, its path is determined entirely by gravity, and sometimes air resistance can be important as well. For our examples in this section, anyways, in 2.2, we're not going to worry about air resistance. We'll come back to it later, and we'll deal with projectile motion with a little more rigor. We'll talk about air resistance in particular. But for now, we're just going to assume that, the situation is like that of a cannonball, where there is no air resistance. Okay. How are we going to model these things? Well, let's talk that through. How to model projectile motion. Well, it turns out, projectile motion, there's a reason that we start with projectile motion in physics, and it's because it really does, first of all, it's like a relatively easy example, but second of all, it does really help us to break down motion in 2 and 3 dimensions. Like you get this concept of the x component and the y component being sort of independent. But the way we're going to model it is we'll basically think of the projectile as operating in the xy plane. So we will model projectiles in the xy plane. Now that xy plane will be determined such that it aligns with the initial velocity, right? So we'll have a plane, x and y, which will be oriented such that the initial velocity lies within that plane. Okay, and we'll indicate that the initial velocity is directed, in a direction that is alpha degrees off of the positive x-axis, right? So you can kind of think of all of the projectile motion as operating within this plane. Now, it turns out that if you ignore air resistance, then truly this thing will operate. It'll go up in a straight line and then down in a straight line, right, within this plane. It's not going to veer off into the z direction, right, if there's no wind resistance. Now, if wind resistance is something to be concerned about, then you might have shear, and you might see the cannonball veer off the plane. But for our purposes, we're going to ignore that as a potential. Okay. Now, the key, as I already kind of indicated, the key to modeling projectiles is to understand that the x and y motions act separately. Is to note that the x and y motions are separate. Right, so we can think of the x motion as doing a certain thing. We can think of the y motion as doing a different thing, and the two of them can be thought of as independent. So what's happening in the x component? Well, the x component has a velocity that's given to it, an initial velocity, and that velocity is constant. So the x component has constant velocity. And what does that mean? Well, I mean, the implication there is that the acceleration in the x direction is 0. So the x component has 0 acceleration. Now the y component is different. The y component has constant acceleration. Right, so obviously the velocity will vary in the y direction. But the y component has constant acceleration, and ay is equal to negative g, right? So g is the only acceleration operating on a projectile, right? And so you really have two kind of simple models that you have to contend with. In the x direction, it's constant velocity, right? So it's, that's as straightforward as it gets. And the y direction, you have varying velocity, but it varies according to a constant acceleration, right? And so that's nice. So projectiles effectively have horizontal motion of constant velocity and vertical motion with constant acceleration. So kind of to summarize, horizontal, let me flip pages here. So the horizontal motion is constant velocity. And the vertical motion is constant acceleration. Right? So here we would say ax equals 0 and ay equals negative g, which we know is equal to negative 9.8 meters per second squared. Okay, so that's the basic setup. Now let's kind of try to draw this and picture why this might be, how this works. Right, so we'll say that we have some projectile that's given an initial velocity, right, and we'll coordinatize this at in the xy plane with the origin being 0, 0. Okay. Right, so we've got an initial velocity, which we'll call v naught. Okay. And acceleration is, as soon as the clock starts running, acceleration is going to be downward and constant. Okay. Now, we know that initial velocity is going to have an x and a y component, right? So there'll be some initial v naught x, and there'll be some initial v naught y. Okay, and the path of the projectile, we'll just kind of draw it in, is going to look like that. Now, what's going on at this point in its flight? Well, we still have the same amount of acceleration downward, right? Gravity's pulling on this thing the same degree that it was initially. The velocity is change directions, right? So maybe it looks more like that now. The x component of velocity is the same as before, right? So these are supposed to be the same length here. But the y component of velocity has decreased, right? The magnitude of that velocity is shrunk down, right? And that's particularly because the acceleration is operating in the opposite direction as it. So it's slowing, gravity is slowing the ascent of this object. Okay, at the peak here, velocity looks like that. The velocity is entirely in the x direction. Right? Acceleration is still pulling the thing down at with the same amount of force. What about the vertical? So the y component of velocity. The y component of velocity is 0 at the top. Right? So we'll just leave it off the picture. Then what starts to happen on the other side of the peak here? Well, over here again, we've got our velocities moving like this. Our x component of velocity looks like this, same as always. Right? But now we've still got our acceleration pulling us down, same degree, but our y component of velocity is pulling us down. I shouldn't be denoting that as v naught y. So our y component of velocity is now changed directions and is in the direction of the acceleration, right? So our acceleration and velocity directions are aligned, so that means this thing is going to continue to speed up, right? And then we know, of course, that's just going to continue until the thing hits the ground. Right? And all throughout this entire flight, the x component of velocity continues to remain, it's constant, right? So constant x direction of velocity. Those are all the same. It's only that y component of velocity that's changing throughout the flight. Okay? So that's kind of the idea. Now hopefully that's relatively clear. So x component of velocity stays constant throughout the flight of the object. The y component of velocity changes due to the acceleration of gravity. Okay, and so let's consider the x motion. Let's kind of pull in some of our kinematics equations and consider what we're dealing with here. So let's consider the x motion. Well, what's happening? So velocity in the x direction, we know, we saw it is equal to whatever the x component of the initial velocity is, it remains constant throughout the flight. This is, of course, only true in the setting where air resistance is negligible, which we're assuming that is the case here, as is the case with cannonballs. Right? The wind resistance on a cannonball is so negligible that you can ignore it. So our velocity in the x direction is always equal to this constant initial velocity. What about the x position? Well, it's going to be whatever the initial position is plus that initial velocity times whatever duration the projectile spins heading in the direction, right? So the x position is basically just its starting position plus v naught x times the time. So that's the simple x direction. What about the y direction? What's the y motion look like? Well, the velocity in the y direction will be equal to whatever that initial velocity is, that the initial y component velocity, minus g times t, right? So we saw up here, you've got some initial velocity. That vector is going to shrink, so it starts out looking like this, then it shrinks down a little bit, then it goes to 0, and then it flips directions, and it increases as the cannonball falls back to the earth. Right, so that's just a simple start with some initial velocity and let acceleration act on it over an interval of time. So Vy is equal to V naught y minus gt. So it really is plus at, but in this case, the acceleration is negative g. And what about the position? Well, y would be equal to its initial position, y naught, plus V naught y times t. So its initial position plus its initial velocity times time plus the acceleration term, right? So that would be minus 1/2 gt squared. Okay. Right, so these are fundamentally kind of this is sort of the setup you would want to start with. Now, initial position, y naught and x naught, are usually taken to be 0, 0, right? So usually we'll coordinatize the problem such that the initial position is the origin of the xy plane. And so typically this can be rewritten as v naught x times t, and we can ignore the y naught term here as well, and this would be v naught y t minus 1/2 gt squared, right? So that's usually what will be the situation. Now, of course, if you have to think of it differently, that's fine, but generally speaking, that's how it's going to work. Now, with regard to this initial velocity, what we'll have to do here is, I mean, usually we'll be told that a projectile leaves a cannon. We'll say something, the problem statement will sound something like this. A projectile leaves a cannon with such and such a velocity, leaves a cannon at 20 meters per second, 53 degrees off of the horizontal, right? So we're just told the initial velocity, the magnitude of the initial velocity. What we have to do is break down the components. So usually we're given the magnitude of the initial velocity and a direction relative to the horizontal. That's usually the way the initial velocity is articulated to us. And so what we'll need to be able to do is break that initial velocity into its x and y component. So we'll need to break v naught into its x and y components. And that's pretty simple to do. It's really just a trigonometry exercise, right? So we've got some initial velocity, right, which I'll just call v naught, and we're told that it is at an angle relative to the x-axis, alpha. All right, so this would be like your x-axis here. And so what we need to know is what's the x component of the velocity, and we need to know what is the y component of the velocity. Okay, and so you can think of this as forming like a right triangle, right? And so we know that the cosine of alpha, right, the cosine of alpha is equal to v naught y, so that would be the opposite over the hypotenuse. Now what's the hypotenuse? The hypotenuse is v naught, and the opposite is v naught y. So this would be v naught x for cosine. V naught x, so adjacent, over v naught. Right, so whatever this number is, you tell me, I can use trigonometry to determine the x component. So v naught x, the x component of the initial velocity, is equal to whatever the magnitude of the velocity is that you tell me, times cosine of the angle alpha. Okay. And similarly, I can get the y component of the initial velocity, right? So the sine of alpha will be equal to v naught y over v naught, right? And so I can solve that for v naught y, and I get v naught sine of alpha. Right, so we'll want to use these two expressions and kind of plug them into our into our kinematics equations. And so in totality, what do we have here? What are the basic motion? What are the basic motions here? So for the x coordinate, for the x motion, we'll say I've got the x component of velocity is equal to v naught x, which we've just shown is v naught cos alpha. And for the position, x will be equal to v naught x times t, which we know is v naught cos alpha times t. Okay, so that's our x motion. And then our y motion, I'll do it down here. Our y motion would be v sub y is equal to v naught y minus gt, and now we know v naught y is v naught sine of alpha, and then minus gt. All right. And then y, the y component of position, would be v naught yt minus 1/2 gt squared. And so we have to replace the v naught y again with this trig expression. So v naught sine of alpha times t minus 1/2 gt squared, right? And so these are the expressions that we'll want to use when we're solving projectile motion problems. Okay, so let's continue. So hopefully that's straightforward. I think, these, if you've practiced your kinematics and you're following the trig argument, and the picture that we drew before is straightforward, this should be relatively easy to digest. Now I do recall when I first really kind of thought about projectile motion in my undergraduate physics days, I do remember thinking, my God, how convenient. This is so convenient. The fact that you can just that you can think of x and y as being completely separate. When you watch the ball fly through the air, you certainly don't think about it in those terms. But I do remember this being kind of an aha moment for me personally when this material was expressed to me. I was like, wow, that's fantastic that you can think about those two as operating separately. So that's the basic setup of the basic modeling. Now, there's additional items that we can get from these expressions, right? So a couple of additional items that we can talk about is, so at any time, the distance from the origin to the projectile can be calculated, right? So I've got some projectile motion, right? Here's my origin. Or if I want to know how far away from the origin I am at this particular point, and I'm specifically wondering, what is that straight line distance? Well, I can use just the distance formula in the xy plane, right? We know that d would be equal to x squared plus y squared, the square root of that thing, right? That's just the distance. Very familiar to us. And that'll come up. That'll be a question that we'll want to know, right? What's the distance the straight line distance from the origin? Another thing that we'll wonder about is the speed of the projectile. So at any given point in the trajectory, there's some speed, right? The object's velocity has magnitude and direction, but there's also just a speed. So what's the speed of the projectile? And that, of course, is given by the magnitude of the velocity vector. So the speed at a particular time is just going to be the magnitude of the velocity vector, right? So we know, of course, that that is equal to the x component of velocity squared plus the y component of velocity squared, and then you take the square root of that. That's the magnitude of the velocity vector, also known as kind of the norm of the velocity vector. The direction of the object's velocity is another question that we'll see. Another item we'll be asked to calculate. So what is the direction of the object at such and such time? Now, usually when we try to describe the direction of the object at such and such time, the best way, the most convenient way to do it would be to give the angle that the velocity vector makes with the positive x-axis. So the direction of the object is best articulated using alpha, where alpha, so if the projectile is in the air and it's moving in this kind of an orientation here, we'll have alpha be the angle that the velocity vector would make with the positive x-axis. So the angle off horizontal basically would be another way to say it, i.e. the angle off horizontal, right? So what's the inclination horizontal relative to the horizontal, right? And so we know that that is going to be equal to just, so the tangent of alpha would be v sub y over v sub x, right? And then, of course, we can use the inverse tangent to solve for alpha. So alpha will be equal to that inverse tangent. Okay. So that's another piece of information that we can pull off of the velocity vector, the components of the vector. Right, so you see, hopefully you're beginning to kind of see that really projectile motion is just, it's just the algebra that you're kind of used to working with. It's just that operating inside the Cartesian plane. You got distance formulas, you've got norms, you've got a little bit of trigonometry, but it really is the algebra that you're hopefully familiar with by now. So let's do an example of kind of how this stuff can look in, what kind of problems can we expect to this type of model to address. So let's start with a straightforward example. Well, I think this one is actually less straightforward maybe than the cannonball, but I think it's a good example to start with. So we'll say that a car rides off the edge of a cliff. So a car rides off the edge of a cliff. All right, so two F's there. All right, so you've got some kind of a cliff here, and you've got this car barreling towards the cliff here, and it's just going to drive right off the cliff, right? So we'll say a car rides off the edge of a cliff. Just at the edge of the cliff, the velocity is horizontal. So just at the edge of the cliff, the velocity is horizontal, right? That would be the case, right? Certainly the velocity does not have a y component if the car is literally just driving in a straight line, right? So the velocity is certainly horizontal. So just at the edge of the cliff, the velocity is horizontal, and then let's put a magnitude on there with a magnitude of 9.0 meters per second. Okay, so we know what's going to happen, right? The car is obviously going to follow a path that looks a bit like this, isn't it? It's going down, right? But it's going to shoot off the edge of the cliff for some distance. Eventually, though, the car will be falling entirely down, right? Okay, so what are we interested in? Let's find the position, distance, so the position and distance from the edge of the cliff so we're going to find the position and distance from the edge of the cliff and the velocity. Let's do that too. After 0.5 seconds. Okay, all right, so I want to find the position, the distance, and the velocity after 5 seconds, or half a second. Okay. All right. Well, let's consider the x and y coordinates. Now, let's just, for the purposes of our model here, let's think about what we mean by x and y distance. So there's x, right? And we'll take this to be 0, 0 when the car leaves the edge of the cliff. And so x is going to be in the positive direction. Now here, in this case, y is actually going to be a negative value. Right? So, I mean, if the car had wings, perhaps y would be positive, but because obviously it doesn't, it's just going to head down, and right? So the y component of position will be negative. Okay. And so that's the setup. That's the setup, and here's our initial velocity. So the other nice thing about this problem is that the initial velocity is entirely horizontal, which means the initial velocity in the y direction is 0. And so the entirety of the magnitude of the velocity, the 9 meters per second, is all in the x direction. There's no y component, right? So we'll do an example next after this where we have to break down the initial velocity. But for this example, you don't have to worry about the initial velocity. You don't have to separate out that magnitude into the x and y components because there is no y component. All of the magnitude is in the x direction. Okay, so let's consider the x and y coordinates. Okay, so let's consider the x and y coordinates. So what is x? Well, x is equal to v naught x times t. And so we know that the initial velocity in the x direction is 9 meters per second and times t. So the position will just be 9 meters per second times t. So meaning that we will just be further and further. So our distance from the cliff, our horizontal distance from the cliff, is purely a function of time, right? It's 9 meters per second times however long the car is airborne. What about y? Well, y is going to be equal to v naught y times t minus 1/2 gt squared. Now, the initial velocity in the y direction, as we just said, is 0. Right? The car doesn't have any y component of velocity. So what we and we know that g, of course, is 9.8 meters per second squared. So this all basically boils down to negative 1/2 times 9.8 meters per second squared times t squared. Okay, so it starts with no initial velocity. The y component has no initial velocity, but it's going to gain velocity in the negative y direction. Okay, and so we can, from these two expressions, we can calculate the position, right? So we can find the position of the car at half a second into its launch. So at t equals 0.5 seconds, then x is equal to 9.0 meters per second times 0.5 seconds. And so you do that math, you can see that that's 4.5 meters. And then y is equal to negative 4.9 meters per second squared So just taking half of 9.8 here, apologies, half of 9.8 times 0.5 seconds squared, right? And if you do that math, if you multiply this all out, you should get something like negative 1.2 meters. Okay, and so the car has traveled to a position that is 4.5 meters in the x direction and negative 1.2 meters in the y direction. Right, so this would be 4.5 and this would be negative 1.2. So that's where the car is relative to the origin point here, 0, 0, at, 1/2 of a second into its launch. Okay. What about the distance from the edge? Well, what is that even asking? The distance is this thing, right? It's the straight line distance. What's the distance? The distance, well, the distance is, so d is equal to the square root of x squared plus y squared, those being the positions. And so this is just 4.5 meters squared plus negative 1.2 meters squared. Take the square root of that. And you see when you calculate all of that, it's 4.7 meters. Right? So it's 4.7 meters from the edge of the cliff. Right? The horizontal distance is 4.5, and then some additional distance is needed to in the y direction. Okay, so that's the distance. And then the last thing that we're interested in is, what is the velocity? How fast, well, what is the velocity both in terms of direction and magnitude? What's the velocity at t equals 0.5? So what is v of 0.5 seconds? What is that velocity? Well, to solve that, we need to just pull in our velocity expressions, right? So we said that the x component of velocity is constant, v0x, and so that's 9.0 meters per second. And we said that the y component of velocity would be v0y minus 9.8 meters per second squared times t squared. Right, and so that one actually cleans up. This is 0. And so this is just negative 9.8 meters per second squared times t squared. And so the velocity at 0.5 seconds in the x direction is equal to 9.0 meters per second. And the velocity in the y direction at 0.5 seconds is equal to negative 9.8 meters per second squared times 0.5 seconds squared. Right, and then if you do that math, you will see that this gets you negative 4.9 meters per second. Okay, so these two components indicate the velocity. So the velocity at 0.5 seconds is equal to 9 meters per second in the x direction and negative 4.9 meters per second in the y direction. Okay, so that's that. Excellent. Let's do one more example. We'll do kind of the classic example, and that's the baseball trajectory example. So in this case, we're going to model the flight of a baseball. So a batter hits a baseball so that it leaves the bat with an initial speed of 37 meters per second at an angle alpha equals 53.1 degrees. Okay. All right, so this is the classic baseball question. And so let's just draw a picture here just so we can situate everything. So the initial velocity is given as 37 meters per second. That's the magnitude of the velocity. We're not told what the components are, but that's the magnitude. And we're told that alpha is equal to 53.1 degrees. Okay, and so you've got, ground level here. So this thing is going to go tearing off of the bat, and it's going to follow a path that looks a bit like this. Right, and we'll take this to be 0, 0. And so what we need to, what do we want to answer with this? Well, there's kind of three pieces to the question, right? And there's lots of things you could ask. You could ask where is it at any given time. You could ask what the speed, the distance from home plate, blah blah blah. But we're going to ask kind of the three classic questions. Okay, so the three classic sort of questions that you want to ask. The first one is you want to be able to calculate position and velocities at some time. So what is the position and velocity at we'll say 2 seconds, right? So 2 seconds after the ball is hit, where is it in this trajectory? Is it out here? Is it closer to here? Is it at the top? Is it hit the ground already? Where is it? So that's the first question. The second question, we want to know when the ball reaches its highest point. When does the ball hit its highest point? Right? So when does it hit its highest point? And then also, what is the height? Right, so basically we're asking, what is this height? Right, so that's a height. We'll say that's the highest point. What height? What is that height? How high does the ball go? And then also, when does it get there? Like, when does it actually get to that height? Right, so that's another classic thing that you can do here. And then finally, the last thing we want to know, what's the distance from home plate when the ball hits the ground? What is the distance from home plate when the ball hits the ground? Right, so obviously it's going to hit the ground right about here. What is this distance? Right, so how far is the hit? Right, so how far does the ball go? Okay. All right, very good. So that's the basic, those are the three kind of classic questions you would want to be able to answer. And this is a good test of, do you understand the mechanics of projectile motion? This type of question gives you a good read on that. So obviously for this problem, there's a couple of things we want to stress, like a couple of assumptions that we'll have in place. So first thing we're ignoring air resistance. Though, in the case of baseball, in reality, air resistance probably is not negligible. But for our purposes, we're just going to assume that it is. A baseball is relatively light, so the air can certainly shear. It can certainly be deflected off the XY plane by air resistance. Also, the X component of velocity can certainly be impacted by the ball cutting through air. So we're going to ignore it for now, but just know that I'm aware of the fact that hitting into a wind is different than hitting with a wind at your back, right? In baseball. So we'll also consider the initial velocity to be at ground level, right? As I've drawn it. Now, in reality, when you're batting, right, you're going to be a little bit off of ground level. But just to make the calculations more straightforward in this initial example, let's just assume that let's just model the ball from ground level. Okay. All right. So what is the initial velocity? That's the first thing we have to break down. So when we're given a velocity like this and an angle of inclination off the x-axis, we need to figure out what's the x and y components of velocity. So we need to identify the initial velocity vector. Okay, so v naught x we know is equal to v naught cos alpha, and v naught y is equal to v naught sine alpha. So just remember, so you've got v naught, you've got alpha, that's a 90-degree angle. So this would be v naught y, and this is v naught x, right? And so you will probably just end up memorizing these things, but just know that if you can't remember, you could always just pull out a triangle and figure out the trig that's required. So we can break the velocity down using this expression. And so we start with 37 meters per second. That's the given magnitude of the velocity. And then times cosine of 53.1 degrees. That's the angle that we're told, right? And then for the y component, it's the same calculation except with the sine. Right, and so when we do that, we see that the x component of velocity is 44.4 meters per second, and the y component of velocity is 39. Or sorry, oh, I wrote that wrong. Sorry about that. I looked at the wrong thing. 22.2. 22.2 meters per second. That's the x component of velocity. And then the y component of velocity is 29.6 meters per second. It would be quite a trick if you could get 44 meters per second out of 37. But anyways, so the x and y components of velocity have to be less than or equal to the overall magnitude, obviously. So the ball is moving at 22.2 meters per second in the x direction, and we know from our models of projectile motion that it will continue to do that until it hits the ground, right? So this 22.2 meters per second is constant throughout the entire flight. The 29.6 will change as gravity works on it, right? So this is the y component of the velocity. This is how much it's traveling, the speed that it's traveling in the y direction, and that'll first slow down and then it'll speed up after it hits its peak. Right, so let's talk about what happens. Let's talk about part A. So part A is we want to know the position and velocity at t equals 2 seconds. Okay, t equals 2.0 seconds. So let's start with the position. So x is going to be equal to v naught x t, which in this case is 22.2 meters per second times 2.0 seconds. And so there's that 44.4 meters. Okay. What about the y position? So that'll be v naught y times t minus 1/2 gt squared. Okay, and so we can plug all of those things in, and we get v naught y, we just calculated as 29.6 meters per second, and then that's for 2 seconds, and minus 1/2, and then it's 9.8 meters per second squared times 2.0 seconds squared, right? And so all of that gets you 39.6 meters. Okay, so the position, so r at 2.0 seconds is 44.4 meters in the x direction and 39.6 meters in the y direction. So that's your position at 2 seconds. Okay, and so what about the velocity? So the velocity, the x component of velocity, we know is just constant. It's the initial velocity in the x direction. So that's 22.2 meters per second. That's not changing. What about the y component? Well, it's going to be whatever the initial y velocity is minus g times t, right? So it starts out with an positive initial velocity. It's headed in the upward direction, but then gravity will work on it. It'll operate on it in the opposite direction over some interval of time, and so it'll slow, basically. Or potentially, if we're past the peak, it'll be speeding up. But let's put it all in here and see what the case happens to be. So we've got 29.6 meters per second minus 9.8 meters per second squared times 2.0 seconds. Okay, so you plug all of that in and you'll find you get 10 meters per second. Okay, so the velocity at 2 seconds is equal to 22.2 meters per second in the x direction and 10 meters per second in the y direction. So the ball is still headed upward, right? The fact that this velocity in the y direction is positive means the ball is still ascending, right? It hasn't reached its peak yet. So we know for part B that we're going to be looking for that peak. That peak has to be greater than 2 seconds, right? So it's still traveling upward at 2 seconds. Okay, and so there's part A. Now, what about part B? So part B asks us to find the time when the ball reaches its highest point. So when does the ball reach its highest point? So when does that happen? Well, how do we think about this? The way to think about it is to recognize that the y component of velocity is going to be 0 at the highest point in the ball's trajectory. So the y component of velocity will be 0 at the highest point. Okay. And so basically what we can do is we can set the y component of velocity, which we know is equal to v naught y minus gt. We can set that equal to 0 and solve for t. Right? So let's see. So, well, t then would be equal to, we could kind of do the algebra first, so we could get negative v naught y over negative g, which is just v naught y over g. Right? So t would be equal to 29.6 meters per second divided by negative 9.8 meters per second squared. And so you can see the meters and the seconds canceling, you're left with the seconds. And if you do this math, you'll see that it is 3.02 seconds. So just a fraction over 3 seconds, a fraction of a second, 3.02 seconds, that's when the ball hits its peak. Okay. So then what is the height that the ball achieves? Right? How high does the ball, what's the highest point in the ball's trajectory in its path? Well, that can be just a simple, think about the y position, the y component of position, and just plug in 3.02 seconds. So the height will be equal to basically v naught y times t minus 1/2 gt squared. Okay, and so that's going to be what? 29.6 meters per second times 3.02 seconds minus 1/2 of g, which is 9.8 meters per second squared, times again 3.02 seconds squared. And so everything will cancel out here, and you're going to get meters. And so do that math, and what you'll find is you get 44.7 meters. Okay, and so the maximum height of the ball's trajectory is 44.7 meters. So this would be 44.7 meters, and that's going to happen at t equals 3.02 seconds. Okay, very cool, very cool. And then finally, the last piece of information that we're interested in is how far does the ball fly? Right? How far? What is this distance here? So here's home plate. Here's where the ball hits the ground in the outfield. How far away? What's the straight line distance between home plate and the outfield? So to find that horizontal range, we need to first find out when the ball hits the ground. Okay, so This is, can be thought of as the y-coordinate of position. We need to know when the ball hits the ground. Okay, so we need to know when that happens. That's the y-coordinate of position. So y equals 0. So when is the y-coordinate of position equal to 0? Well, it's obviously equal to 0 at the onset when we first hit the ball, but it's also going to be equal to 0 later on in the trajectory. So y equals 0, and we know that that's going to be equal to the initial velocity in the y direction times t minus 1/2 gt squared. And so we can, really what we're interested in here is v naught yt minus 1/2 gt squared equals 0. And you can do some factoring here. If I factor out a t, so I got v naught y minus 1/2 gt equals 0. Now, just from your algebra days, you'll recognize, oh, I've got two solutions. This is a quadratic. All right, so one of the solutions is t equals 0. That's this part. And the other solution is v naught y minus 1/2 gt equals 0. So obviously, this is when the ball is at home plate. This is the home plate. This is the home plate time. So that's when time is equal to 0. We haven't hit the ball yet, or we're just hitting the ball. And over here, this is where the ball is landing in the outfield. So this is the relevant one. This is when the ball lands in the outfield. Okay, so that's the one we want. And so we can just kind of solve for t here. All right, if we do all of that, we'll see that t is equal to twice v naught y divided by g, right? And you can do that algebra on your own and see that. But if we plug in all of our quantities, 2 times 29.6 meters per second divided by 9.8 meters per second squared, then you'll see that this is like 6.04 seconds. Now, does that make sense? Yeah, that makes sense to me. That's twice the time it takes to get to the top, right? So we saw that it took 3.02 seconds to reach the top of the trajectory. It's going to take that time again to reach the ground. So that's a very intuitive response. Now, that just tells us the time that it takes to hit the ground. What we really want to know is how far away from home plate is it, so we can take this time and plug it into the x component of position. So x is equal to v naught x times t, so the initial velocity in the x direction times however long it spends under that velocity, right? And so 22.2 meters per second times 6.04 seconds. It's so sloppy. 6.04 seconds. And if you calculate 22.2 times 6.04, you get 134. So 134 meters. That's the distance. So we hit the ball, travel some path, and it lands. All right, and that distance is 134 meters. I think that's a pretty good hit. Okay. All right, very good. Very good. That is where we'll end it. So that is projectile motion, and we'll do lots more with projectile motion, certainly. But in the next section, we're going to shift our focus to another kind of motion that's sort of fundamental, and that is circular motion. Okay, so until then, take care.